Thermal analysis using PTC Creo. In this problem, we have given an aluminum fin, which is commonly used to dissipate heat from electronic module, and the boundary conditions are the ambient temperature is 28 degrees Celsius, and the heat flux, which is given as 1000 watt per meter square at the base of the fin. The base is given here. That means this base is pasted over the heat source, which is maybe a processor of a computer, whatever it is, the electronic module that we used in our appliances. And heat transfer coefficient is given as 30 watt per meter square degree Celsius. That means the cooling of the electronic module is by means of the conductivity of the aluminum and also the convective heat transfer from the surface of the fin to the atmosphere. And we are considering a steady state condition of heat transfer from the fin to the atmosphere. And in this problem, we need to find the temperature distribution. That means at the source or the base of the heat sink to the extreme end of the fin, and also the heat flux distribution. The geometry is given 22 meter wide and 15 mm thick, and the height of the fin are 8 mm, and the thickness of the fins, every fin is 1 millimeter. So let's create the part in PTC Creo. So control new, and let's name the part as fin. Let's check the unit, which is millimeter Newton second. It's already okay. So let's take the front plane and go to extrude, take the line command, this is 22, and this one is 3, and the height is 3. Let me check. Yes, the height is also 3, and the height of the fin is 8. So this will be the dimension. Right. The thickness of the fin is 1, and the spacing between the fin is, it's 2 mm. As per the figure, it is 2 mm. So let me complete the fins by means of the 2D sketch, or you can use the pattern itself. We have the equal constraints. We are getting equal constraints here, so I can complete the drawing with the equal constraints only. This is equal to the left side, equal constraint. Right. So this will be the geometry. So I can extrude to the thickness of 15 mm. Click on OK. This fin I have already created. So we can jump to the application, go to applications, simulate itself. The structural and thermal simulation are included in a single module, which is called simulate, and we can switch to thermal mode. Right. So the boundary conditions are the heat flux which is given at the base of the fin is 1000 watt per meter square. So let me assign that. Go to heat. So here the value is asking is heat in watt only. So I need to change it to load per unit area, watt per meter square, and the given value is here, watt per meter square, and the value is given as 1000. So let's check the surface also. The heat flux is given at the bottom of the surface. So just check the preview. You can see the heat flux applied at the bottom. Click on OK. Right. Then the other condition is heat transfer coefficient, which is convective heat transfer coefficient on the surface of the fin is 30 watt per meter square degree Celsius. So go to convection or convection condition, and the heat will be dissipated through the entire surface of the fin except the base, because the base is based on the electronic module which is producing the heat. So select all the surfaces here, this one, every surface is possible. Okay, every surface except base is selected, and let me check the values. Heat transfer coefficient is 30 watt per meter square degree Celsius. Okay, watt per meter square Kelvin is the only unit available, but which is per degree Celsius, and degree Kelvin will be definitely same. If you try to convert both the units, the value will be same. And the bulk temperature, that means the ambient temperature, which is convection is happening, is 28 degrees Celsius. So the value is 28 degrees Celsius itself. Right, so let's check the preview of convective heat transfer and the ambient temperature itself. Okay, so click on OK. Now all the boundary conditions are applied to the model. Let me assign the material then. We have the material library, legacy materials. The assigned material is aluminum. We have two types of aluminum here. One is aluminum 6061, the other one is 2014. Let's check the 2014. We can see the thermal properties of the aluminum over here and the structural as well. So double click on that material. So aluminum 2014 is in the model. Click on OK, then go to material assignment. The material is already assigned to that model, so click on OK. Now the material assignment is completed. Then similar to the structural analysis, go to analysis and studies, create a new steady state thermal analysis, or you can go for the transient thermal, but now we are considering the steady state only, which is the simple one. Then click on OK. So run the simulation. Do you want to run interactive diagrams? You can either go for yes or no. Now the simulation is completed. Then go to review results. We have which is similar to the structural analysis. We have fringe vectors graph model. So we'll check with the fringe. Click on display locations. Let me check the animate button or not. Okay, here the temperature is given in degrees Celsius. That means at the source the temperature is 33, and at the topmost end, that means at the end of the fin, the temperature is 33.23, because aluminum, which have a higher conductivity, that means higher conduction is happening. The fringes, the range of fringe is very low, but still it is showing different colors, but the range is very low. So temperature distribution is found. This will be the temperature distribution, or you can animate that. Okay. Then the second one is heat flux distribution. So go to the display tab, click on flux, and it is asking for the axis or the direction of heat flux. Actually, the heat flux is applied at the base and the heat transfer is happening to the fin, so it will be the y-axis. According to my model, it is y-axis. You can see that, right? Heat flux is also given. Or the assigned heat flux as per the question was, it is watt per meter square. So the output is in another unit, so I can convert the unit to, just a second, quantity watt per meter square. Okay, and show. Now it is showing, it is the maximum flux is at 3482 watt per meter square. All right. So now let's check the vectors as well. Click on vectors, the same unit. Okay, and go. You can see the vectors, how the convection is happening, and let's check to animate. Okay, and show. Go to front view to get the clear picture of vectors which going, right? Then as we discussed in the structural analysis, you can take the printout of both the results, taking the print of that in JPEG format.